this sequence, see if we can find a formula for this sequence. 0, 4, 18, 48, 100, 180, 294. So, looks kind of harder, right? So I want to show you something that's really interesting here about these. What if I took the difference of each of these? So if I said this equals 4 minus 0, and then did the same thing with all of these. So 4 minus 0 is 4, 18 minus 4 is 14, 48 minus 18 is 30, 100 minus 48, 52. So what would these numbers represent? So I'm looking at each of these changes, right? So the change from 0 to 4, the change from 4 to 18, the change from 18 to 48. As your index changes by 1. What would these numbers be like? How much, what? No, well, it's how much it changes, okay, but what? For a change of 1, right? For a change of 1 in the index. What is that? How much a value changes for a change in 1 of the independent variable? What's that? Yeah, this is the rate of change, right? Isn't this the rate of change of this sequence? Let's do it again. So I'm going to get the rate of change of that. That. And what do you notice about that? 10. So this is now the rate of change of the rate of change, like the second derivative, right? It's kind of like the second derivative. So this is, what do you notice? It increases by 6 every time. What kind of function is the rate of change of the rate of change? If it increases by 6 every time, is that a constant function? No. Linear, constant rate of change, right? Constant rate of change. It goes up by 6 every one. So if this is linear, constant rate of change, what is this? Not exponential, quadratic, and our original is cubic. So by looking at the rate of change of this and looking at the rate of change of that, we found I have a linear progression here. Means this is a quadratic progression. Means this is a cubic progression. This helps, right? This helps figure out the formula. So I'll insert a column here. So let's just start by listing the cubes of these numbers and see if that helps come up with a formula for this. So I'm going to do the cubes of these. So I'm going to say equals this cubed. Doesn't like it. Equals that. There we go. And I'm going to take the cubes of all those numbers. And again, what are we interested in this? So now I've got the cube of my index, and then I've got 8. And 8 gives me 4, 27 gives me 18, 64, 48, 125 gives 100. So now can we maybe see what the formula is to get this? So this is our actual sequence, right? What mood are we in today? A blue mood. Okay? So we're trying to figure out the formula for this particular sequence here, and we know it's cubic. We figured that out by rate of change. And here are the cubes of my index. 1, 8, 27, 64, 25, 216, 343. So how can I take the cube and continue to work to get this? So 8 to 4, 27 to 18, 64 to 48, 125 to 100. Anybody see it? Some people are seeing it. Yeah, some people are seeing it. Do you notice that, what, this is 4 greater than 4, and this is 9 greater than 18, and this is 16 greater than 48, and this is 25 greater than 100, so formula is I cubed minus I squared. Do you see it? And so could we have come up with that without knowing that it was cubic in the first place? Maybe a different way, but I just wanted to demonstrate that idea that this is I cubed minus I squared. There are other ways to do it, but I wanted to give you this kind of way of using rate of change to figure it out, that it's a cubic and then go from there. Now maybe we needed to multiply these cubes by 2 or by -3 first to get, you know what I mean? So that this was kind of an easier one. So you could have had any coefficient in front of this I cubed. So we just started with a coefficient of 1 to try to figure it out. And it worked in this case because this is moderately easy. Okay, does it make sense? So maybe that will help with some homework problems, okay? Maybe that using rate of change, using differences for a difference of 1, working down to get rate of change. Yeah?
Would this be a viable solution?
Did you get that? I cubed minus I squared?
Yeah.
Yeah, then it's a viable solution.
Oh, no, but I also had a different answer.
What? I times I squared times I minus 1?
No, I had 4 plus 10 plus 6n parentheses n.
4 plus, what is it?
Parentheses 10 plus 6n.
I?
Or I, yeah, and then times I on the outside, all over I, but not.
Well, I mean, if it's right, then the algebra would make it right. And I don't think it can be right because this isn't cubic.
Okay.
Yeah, so the way to test it is, does the algebra work out? And immediately I see that this isn't cubic in the first place. So it's not, and I over I, that just goes away. And then you got 14 plus 6i, which will give you the same thing as this. But yeah, it's possible to have it a different way. Like you might have come up with I squared times I minus 1. And that would be the same. That's the same as I cubed minus I squared. Okay, and so that brings up a good point. In the web, so I just want to say, we're using I to mean the changing index, meaning it takes on all values, 1, 2, 3, 4, 5, 6, 7, 8, okay? That's how we're using it in class. And then we're using n to mean a particular value of I. That's how I'm using it in class. Okay, is that fair? So I means it's the index that changes. It's 1, and then it's 2, and then it's 3, and then it's 4. And then when we use n, we're saying, okay, say I is 3. So that's our value. N is 3. So n is a particular value of I. Web work uses n like I, the way we're using it in class. So when you get to web work, you're going to see lots of n's. And you need to think of those as i's that we're using in class, the changing value. Make sense? So I know that's confusing. But in class, I will mean the changing value of the index. N will mean a particular value of I. In web work, n will mean I the way we're using it in class, all the values. 1, 2, 3, 4. So I just want to get you in that way of thinking. Okay, any questions? Cool, so we're going to talk about, all right, convergence and divergence of sequences in series. An infinite sequence converges, what do we mean? If an infinite sequence converges, if all the terms after some place in the sequence become essentially indistinguishable from each other. So close together that we don't care anymore, that they're not the same. Technically, they're still different. Technically, you can go out to enough decimal places and you can find a slight difference. But it's like, it doesn't matter. They're getting indistinguishably close to each other. Okay, a more mathematical, this is kind of the idea of it. A more mathematical way to think of this is pick any degree of closeness between two successive terms. Like, say, start with 0.1. There'll be some point in this, everyone's just writing and not listening. Right, just do it. Just write so I can talk and you can listen. Okay, so the actual, kind of the mathematical way of thinking about this is you pick some degree of closeness between terms, like say 0.1. Then there's some point out in the sequence where all the terms will be within 0.1 of each other, and then they'll never get further apart. But then you can pick another degree of closeness. Now pick 0.01. Well, you can still go out somewhere in the sequence. You can get out far enough that the terms are within 0.01 of each other. And you can pick any degree of closeness that you want. And you'll eventually find a place in the sequence where the terms are that close and never get farther apart. So you can pick 1 millionth, 1 billionth, 1 trillionth, and eventually somewhere in the sequence, that's how close the terms will be together. But then you can make your degree of closeness as small as you want. That's what a convergence, that's the mathematical idea behind convergence of a sequence. Okay, so in other words, what we're saying is the limit. Okay, so the limit of the function, so this is now the function notation for the sequence, a of I. This is the idea of limit, right? So if a sequence converges, it has a limit. It has a limit. If the sequence doesn't have a limit, if any other thing happens, any other thing, we say the sequence diverges. And there's more than one way that can happen. But it's any other outcome of a sequence rather than converging, the sequence diverges. So examples. This one. This is our first sequence that we talked about. Does the sequence converge or diverge? Do the terms get indistinguishably close to each other? Can we pick smaller and smaller degrees of closeness, and do we get within that? No, right? It's always just jumping by 2. So this diverges. Okay, this was our second one. -3/4, 5/9, -7/16, 9/25, -11, 36, and here was the formula for that. So you can look at the sequence of numbers and kind of scratch your head and be like, but then the formula is really helpful, right? Because now we can go back to like limit back in pre-calculus, or even in Calc 1. In Calc 1 you did limits, and in pre-calculus you looked at these rational functions, right? So in rational functions you looked at what was called end behavior. Like, does it have a horizontal asymptote? Remember this? End behavior of rational functions. And we know what rational functions are from our last unit. One polynomial divided by another. And so what's the end behavior of, so this is linear divided by quadratic, right? 2i plus 1 over I plus 1 squared. According to our end behavior of rational functions, does that have a horizontal asymptote, or does that converge? If you have a linear term in the numerator and a quadratic term in the denominator, do you remember? Converges or not?
Should have a limit of 1, I would say.
Limit of 1. So let's think about this. When we get to, say, I equals 1 billion, we'll have basically 2 billion on the top and basically 1 billion squared on the bottom. What's happening? 2 billion divided by 1 billion squared. 0, right? So this is getting small. And now, so no matter, and if you make the higher, the bigger and bigger that you make I, the more that the denominator squaring it accelerates and makes this thing really small. Okay, so this limit is 0. This converges to 0. So this was this kind of this rule you learned in pre-calculus for a rational function. If the degree of the denominator is bigger than the degree of the numerator, converges to 0, right? What about if they were the same degree? So we'll see more examples. But what happens if they're the same degree in the numerator and denominator? Then the limit is actually, so quick example, say. So let's say. So what will this, if you got 3i to the fourth minus 2 or 5i to the fourth plus I squared, does this converge or diverge? Now the degrees are the same. So again, so let's put a trillion in and see what happens. If you put a trillion in, you get 3 times a trillion to the fourth over 5 times a trillion to the fourth, and a trillion squared is like 0 compared to that. So if you have 3 times a trillion to the fourth over 5 times a trillion to the fourth, that's really close to what? 3/5. 3/5, right? So when your degrees are the same, it will converge to the ratio of the coefficients of those leading terms. If the degree of the denominator is bigger, that's going to go to 0 because the denominator is going to explode compared to the numerator, even if it's getting really big too. And then if the degree of the numerator is bigger, then what? Then your numerator is going to explode compared to the denominator. And what's the conclusion? Yeah, diverges. Just going to get huge, right? Just going to get huge. Okay, so that's kind of just a crash course, but we'll be using that. Crash course in rational functions. That converges to 0. All right, how about this one? Here was the third one we did. We got 2 to the I minus 1 over I. So like 2 to the billionth power over a billion. What do you think is a bigger number? 2 to the billionth or a billion? 2 multiplied together a billion times or a billion? Definitely the former, right? This is going to get huge, right? Compared to, if you multiply the number 2 together by itself a billion times, sorry, a billion minus 1, divided by just plain a billion, that's going to be, it's going to get huge, okay? So this is divergence. Okay, so there's these kinds of problems. There's a common sense aspect to it. There's also some like precise mathematics to it. It's a balance. Okay, you're using reasoning, common sense, but you're going to need some like mathematical proof too. So here's a common form of a sequence, and it's the P sequence. P sequence. I have a 4 and a 6-year-old. I know a different kind of P sequence. All right, so sequence 1 over I to P. This is what it is. It's when you have 1 over I as your index raised to some value P. So the question is, for what values of P is this going to converge? And how will it converge? If I to the P gets really, really big. So then 1 over I to the P gets really small. So what values of P does I to the P get really, really large? That's what we're interested in, because then we'll have a convergent P sequence. Does it make sense? So you're going to write out the first 4 terms of each sequence. So again, see this, think what, right? So when I show you those symbols, All right? Tell me what you should think when you see those things. What do they mean? What do they mean? Okay? And then based on that, we want to try to figure out for what values of p the sequence converges, right? So this is p equals what? What is p equals for the first one? I heard 1, 2, and 3. What does p equal for this p sequence? 3, right? The exponent is the p. What does p equal for this one? 1/2. And this one? -2. Okay, so go. So you're going to write out the first 4 terms of the sequence. Meaning, what you're writing out is what you would think when you looked at those, right? This is what you think when you look at those, all those symbols. And then we're asking, does the sequence converge or not? Lucas, did you get this first one? Can you tell me what the 4 terms are?
Yeah, so it's 1, then 1/8, 1/27, and 1/64.
And then we write ... Okay, next one. Let's see. Yeah.
1 over square root of 2, 1 over square root of 3, and 1/2.
Okay, last one. Yeah.
1, 4, 9, 6, 15.
Okay. Which of these converge and which diverge? Which converge and which diverge? Does the first one converge or diverge? Converges. How about the second one? Does it converge or diverge? So we could let's keep going here. 1 over radical 5, 1 over radical 6, etc. So what's happening to the denominator? Is it getting bigger? And let's just sketch square root. I'm going to sketch square root. It looks like this, right? And does this level off or keep getting bigger? Does it level off or does it keep getting bigger? It keeps getting bigger, right? You're always taking the square root of a bigger and bigger number, so those numbers are going to get bigger and bigger. They're just not going to get bigger as fast as these, right? I cubed, those get big fast. These get big, they just take, it's a lot slower process. But they still get as big as you want because this square root always gets bigger and bigger. Conclusion? Converges or diverges? Converges. Right? These both go to 0. It's just this gets close to 0 much, much faster than this one in terms of for I. What about this? Okay, so now can we come up with some kind of guess at a rule for what would P have to be? What's that? P says positive. What do you say?
Yeah, P has to be
Positive. So, yeah, these were positive. This was negative. Positive means as long as that P is positive, that denominator gets larger. Even if that's a really small positive number, it would get large very slowly, but it would still eventually get large. Because we never run out of i's, right? We never run out of big values of I. We can always find bigger values of I. So for what value of P does I to the P get really big and the reciprocal gets really small? P greater than 0. These are the values of P for which the P sequence converges. P greater than 0. So here's another way to say that. Thus, 1 over I to the P This approaches 0, has a limit of 0, converges to 0. Those are all the same thing. That's what the arrow to 0 means. It means the terms of the sequence get indistinguishably close to 0, or the limit is 0, as I gets big if p is greater than 0. If p is 0, what happens if p is 0? What do we get?
For every value of y, we're going to get a sequence value. We're going to have a sequence with one element.
Right, so we get this, if p equals 0, we get the sequence, what? 1, then 1. Does it converge? Do the terms get indistinguishably close to each other? As close as you want? Any degree of closeness? Yeah, yeah. So that also converges, but it doesn't converge to 0, right? So it's kind of like a trivial case. It does converge, but it just ends up being all ones, and that's kind of like, okay, we talked about it, go on, let's move on, right? So it's like a trivial case. But in order for the sequence to converge to 0, that's what we're more interested in, that converges to 1, p has to be greater than 0. Are we good with these p sequences? Okay, moving on. Okay, a geometric sequence. A geometric sequence has this form. Now, what's different about this? It's not a fraction, of course, but what's the... This could involve fractions. So what's the main difference from a geometric sequence from a p sequence?
So out of curiosity, R is constant, right?
Yeah.
Okay, so in the P sequence, it seems that I is not a negative exponent.
Sure, it could be a negative exponent. I showed you an example.
I mean, it's not written as like a fraction, where it's like 1 over the constant and then your power, right?
Okay, but R could be a fraction.
Oh, okay.
So I could kind of make it look like a p sequence and make it into a fraction. So, but there's really a main difference here between p sequence and
Like with the p sequence, the value that's changing is being raised to a constant, whereas this being a constant is changing.
right. It's which is the exponent and which is your like constant in the situation. In the p sequence, your index was the base, and the constant p value was the exponent. In a geometric sequence, your base is the constant, and the thing that's changing is the exponent, the I. So that's how you identify the difference between a p sequence and a geometric sequence. Is that what you're going to say also? Yeah. All right, so that's how you identify that. If your I is your exponent, that's geometric. If your I is the base and the p is the exponent, like a constant exponent, then you have a p sequence. All right, so now we're asking for what values of R. Does R to the I get really small, or get really big, or stay constant, or do something else? So I'm going to take a test. I'm going to do the same kind of thing you did before. And you got 6 examples now. And so we're investigating these examples to kind of try to come up with try to figure out when is it, for what values of R does a geometric sequence converge? And for what values of R does it not converge? And so here are some examples that will help you determine that. All right, so I'm going to take attendance. You're going to show me explicitly what each one of these means, all 6 of them. Write out what they mean. And then use that to make conjectures about whether geometric sequences converge or not. Okay. Write them all down. I'm going to change the screen here in a sec. Got them? All right, ready, go. So do the math and then compare and contrast and talk and figure it out.
The sequence
Sequence of ones. Is it right? Converges or diverges? Converges to 1. 2 to the I. What do we get? 2, 4, 8, 16, 32. Definitely diverges, right? Okay, next one. 3/4 to the I. First we get 3/4, 9/16.
27 over 60.
This is not. I'll just trust you guys. 27 over 64 then? 81 over. So what are we doing? We're always, so in effect, how are we getting the next term of this sequence, in the sequence? How do you get the next term of the sequence? If it's 3/4 to the I, 81 over what was it? So if I have 3/4, how do I get 9/16? And if I have 9/16, how do I get 27/64? There's just it's a lot simpler than that. How am I always getting the next term? You multiply by the last one by 3/4, right? Because there's one more 3/4 multiplied, right? So the second term is just the first one times 3/4. And then the third term is just the second term times 3/4. Then the fourth term is just the third term times 3/4. That's all you're doing. It's just you just keep multiplying by one more 3/4, the previous term of the sequence. So what effect is that going to have? You're always going to have 75% of what you had previously, right? You keep taking 3/4 of what you had. So what's going to be the result of that? 2? Yeah, that's going to converge to 0. You're always taking a fraction of what you had before. Okay, what about negative 1/5 to the I? Negative 1/5. Positive 1/25. Negative 1/25. Positive. What do we think about this? Converges or not? Diverges. What do you think? Do the numbers get indistinguishably close to each other eventually? Does it converge to 0? Let's draw a graph. So if I put I on this axis, and I put my sequence values on this axis, I have negative 1/5, then 1/25, then negative 1/25, 1 over 625. Is it converging? Definitely, right? Yes, it alternates, but it gets squeezed in at 0, right? It's like getting squeezed in at 0. It gets as close as you can pick any degree of closeness to 0 that you want, and you'll get within there, and you'll stay within there, even though it's still jumping up and down above the axis. So just think of a funnel, right? That funnel will get narrower and narrower, and always funnel you into 0, right? It's going to funnel those numbers right into 0. Okay, what about negative 3 to the I? Diverges. Negative 3, 9, negative 27, 64. And so what would that graph look like? Yeah, so this is going to diverge, and it's going to diverge badly. It even diverges in 2 directions, right? It diverges to positive infinity and negative infinity kind of at the same time, alternating. So this is as bad as it gets for divergence, right? What about negative 1 to the I? Converges. Converges to what?
It depends on what distance you choose, I guess, right?
So negative 1, 1. Negative 1, 1. Negative 1, 1. Do those terms get indistinguishably close to a number? Do those terms get indistinguishably close to a number? 1 and negative 1. Does that sequence converge or diverge? And if it converges to what? What does it converge to? What single number does it converge to? The average? 0? So let's go back to our definition of convergence. Those numbers in that sequence need to get indistinguishably close to a number, meaning I pick a degree of closeness to whatever the limit is, and those numbers will get within that degree of closeness and stay there. And then I can pick a smaller degree of closeness. Does it work? No. Right? So, I mean, you might think 0 because that's the average. Okay? So, say if the limit's 0, that means I can pick a degree of closeness of 1/2. And eventually, all my terms are going to get within 1/2 of 0. Is it right? No. They're always 1 away from 0. Any degree of closeness less than 1, it never gets in even within that. Doesn't make sense. So, big time, diverges. The list of numbers has to get indistinguishably close to whatever your limiting value is for it to converge. It's not happening here at all. It just keeps jumping between 1 and -1. It's not getting closer to any one particular number. That's what converges means. It gets closer to one number and as close as you want to that number. Okay. Any questions on that? So our conclusion. So what's our conclusion about geometric sequences? For what values of R does the geometric sequence converge to 0? How can I get the geometric sequence to converge to 0? What does R have to be based on these examples? Less than 1? -3 is less than 1? Okay, meaning R values between 1 and -1. You have to have a fraction. Remember, this is the idea of repeated multiplication of a number. That's what these sequences are about. So you need, when you're repeating multiplication, you need to keep taking a fraction of it. So what cases was that in these examples? 3/4 and? Yeah, so when you have these examples of repeated multiplication of a fraction less than 1 or greater than between -1 and 1, then you keep cutting it, you keep taking a fraction of it, and those will converge to 0. All right? What about greater than 1? Just going to blow up, right? What about less than -1? Just going to blow up. So then what's left is 1 and -1. 1 to the I? Converges or diverges? Converges to 1. Again, trivial case, right? Trivial case. -1? Diverges. Just keeps jumping. It doesn't get close to a particular number. It doesn't get close to a particular number. So our overall conclusion is? The geometric sequence converges when R is? Converges to 0. Converges to 0 when R is? Between -1 and 1. This idea of the repeated multiplication of a fraction. Or of part, something, a fraction of 1. So in the old days, I don't know if they still do this. In just the handheld calculators, you could say like 2 times, and then you could keep hitting times, and it would keep multiplying by 2, and you could see what the number would do. And so that's exactly what a geometric sequence is. So like if you put in 0.99, and you went times, you would watch 0.9 keep getting multiplied by itself. And if you hit it enough times, what would happen? Times. Eventually it would be smaller. It'd be smaller than the calculator could show, and it would say 0 on the screen. And it would just say 0. You use times, 0, 0, 0. So because it couldn't keep enough decimal places, right? It couldn't keep enough decimal places to make a small enough number. But the idea was you keep multiplying by 0.99 over and over again, and it goes to 0. That's a geometric sequence. So then there's the trivial case that it goes to 1 as if r equals 1. But we don't really care about that. We talked about it. We did that example. We're done with it. Okay? So it's just a trivial case. Okay, so here's kind of a, you're just going to get all kinds of sequences thrown at you, and so here's some just tips. So like a toolbox kind of for analyzing sequences and sequences for convergence or divergence. The first is to look for these two we've talked about. Be on the lookout for geometric NP sequences, because now you know when those converge and when those diverge. Right? You know, so we've got, and make sure you can tell them apart. Make sure when you look at it, you know, oh, that's a P sequence or that's geometric. And that's about which is the base and which is the exponent, right? Okay, use function limit techniques. So I talked a little bit about that. So if your sequence is like a rational function, then you can use those techniques for analyzing rational functions for n behavior. So that's properties of rational functions. That's what I said. Okay, and then there's L'Hopital's rule. Don't have time to, we'll maybe do that on, start with that one on Monday. No, I can just write it down. Here we go. So L'Hopital's rule says that if you have a sequence that's like a ratio of functions, and if that ratio of functions, if both the numerator and the denominator both go to 0, or if they both go to infinity for large values of I, then the limit of that is equal to the limit of the ratio of their derivatives. So you can take the derivative. If you have this situation where you get 0 over 0 or infinity over infinity, you can take the derivative of the numerator and the derivative of the denominator separately. And a ratio of functions, and you're trying to figure out what the limit is, and you get 0 over 0 or infinity over infinity, then you can analyze the ratio of the derivatives, and that will have the same limit as the one you were given. All right, this is not the quotient rule, right? It's not the quotient rule. You're looking at each individually and taking their individual derivatives, setting up a new ratio, new function. That converges to, say, 3, then that converges to 3.